Hello everyone, my name is Amin Nazarzadeh. In this presentation, I'm going to talk about stability analysis for event-triggered nonlinear control systems under denial of service attacks. This work is collaborated with Mohsen Qudrat and Professor Marquez from ECE department at University of Alberta. My presentation is going to cover the following four sections. First, cyber attack in network control systems. Next, our defense strategy and control system structure. Then stability analysis and results. And finally, case study part. In general, cyber attacks can be categorized as deception attacks and denial of service attacks. Deception attacks manipulate sensors and actuators output, while denial of service attack make interruption of data transmission through a network and result in data packet losses, which is shown in figure 1. One way to model a denial of service attack is using a deterministic model, which means imposing a limit on the total length and the number of attack, which is sensible because of limited source of power in the attacker side and network protection layers. There are two main control strategies against denial of service attacks. First, robust control, where a controller is designed to tolerate the maximum possible length of consecutive data losses induced by a denial of service attack. Second, model-based approach, where the controller employs the plant model to generate a prediction of the plant's future output to be used during attack intervals. And our purpose method belongs to the second type. Figure 2 shows the block diagram of our control system structure. The system output is connected to the digital controller, so we can call it as a nonlinear sample data control system. The control U is implemented in a dual mode, event-based fashion. More precisely, the transmission of information between sensors and controllers takes place only at the triggering instance during normal conditions. Otherwise, at the presence of denial of service attack, it has constant rate. The reason that we employ an event-driven mechanism is the flexibility offered by the event-based approach when deciding when to transfer information between system components. The triggering rule can be designed based on an approximate plant model. However, the rule is guaranteed to work for the true nonlinear system. And in this structure, the control system may asynchronously targeted on both side channels. Control system time instance is provided in figure 3. In this figure, point 1 is the successful transmission instance. At this point, the controller receives the sensor measurement and uses it to build the stack control vector and send it to the buffer. The actuator will continue to receive the control signal from the buffer over the finite time sequence. After that, the actuator signal is kept constant until the next successful triggering. Point 2 is the time at which a denial of service attack occurs. At time point 3, event-triggered condition is satisfied, thus leading to a new triggering event. However, transmission is impossible due to the presence of the denial of service attack, and until the end of the attack interval, data will continue to be sent at a constant rate. Based on this observation, we divide the intersampling interval from point 1 to point 4 into 3 subintervals, which the stability analysis of the control system is constructed based off them. We are interested to study input-to-state stability of nonlinear systems under denial of service attack. This strategy is based on analyzing the Lyapunov function growth rate in different subintervals. For example, by using tools from multi-rate sample data control, Lyapunov function derivative is decreasing during interval 1. In the interval 2, there are no new triggering events, and therefore the system remains stable, although with a different convergence rate. And interval 3, the event rule is violated. However, the feedback signal cannot get updated due to the presence of the denial of service attack. Therefore, the Lyapunov function may increases over this interval. Finally, we can find an exponential upper bound for the Lyapunov function valid for all time, and input-to-state stability is obtained if the exponential function has a negative rate. Our main result is providing a relation between input-to-state stability and attack parameters. In the other words, we formulate an optimization problem to obtain the largest possible total attacks intervals such that the closed-loop nonlinear event-based system remains input-to-state stable. In order to have a proper comparison between our proposed algorithm and the previous results, we consider the same system and denial of service attack scenario. Figure 4 shows the successful triggering event over time. White and gray strips represent the time periods where there is no denial of service attack and the attack intervals respectively. In comparison with the previous works, the number of events has decreased, which shows the ability of the event triggering mechanism in managing network usage. Furthermore, the simulation also shows the ability of the purpose method to tolerate larger attack intervals, followed by the fact that the system can work in the open loop mode for a long time. Also in figure 5, we can see the state response of the nonlinear system over time, which is not only reached the equilibrium point, also faster than the result in the previous works. And finally, thank you so much for your attention.